a fifth-year graduate student in my group. He did his undergraduate studies at Washington University in St. Louis, and then came to our department here at Princeton. So Jacob has been working on a project that's a little bit different than what we've been working on, I guess, over the last 5 years. Rather than focusing on how we can expand an enzyme's function using light, what Jacob has been interested in doing is seeing whether we can run photochemical reactions in the presence of enzymes to achieve, I guess, cascade reactivity that would be challenging to achieve with the enzyme on its own. And in particular, what we've been interested in are sort of dynamic processes that we could carry out in solution, and then using the enzyme as sort of the selectivity determining step of the cascade. And so Jacob's work is sort of the first project in that area in my group. It was run in collaboration with our colleagues in the Macmillan group here at Princeton. And so with that, I'll just hand it off to Jacob to have him tell you what we've been up to.
Thanks so much, Todd. Can everybody see my screen and hear me? I'm going to assume probably.
Yeah, you're on.
Okay. Well, yeah, thanks again. First of all, thank you to the organizing committee and Allison for organizing this really wonderful opportunity to share my research and to hear about other people's research over the past couple months and today. It's been really a great opportunity. But like Todd said, I've been working on novel dynamic processes. I guess I'm start by preaching to the choir a little bit and pumping up biocatalysis and why it's important and interesting. Of course, biocatalysts, they work under mild conditions and they're sustainable compared to metal catalysts. And of course, a linchpin also being that they can be highly evolvable if they're not already highly selective for a particular transformation. Just as an example, in industry of biocatalysis, this synthesis of Lyrica by Pfizer uses this malonate ester that they can subject to this lipase to hydrolyze one enantiomer quite selectively. And this is an example of a kinetic resolution mediated by a biocatalyst. And the way that these work is that you have a racemic mixture of starting materials, and a biocatalyst can pick out one enantiomer and get you to the desired product, but the other is left unreacted. So you can get very high selectivities, as Pfizer did for their product. The only issue with a kinetic resolution is that you're maxed out at 50% yield because you have your unreactive starting material enantiomer. So Pfizer has to subject this to a racemization protocol in a separate step, and then resubject that now racemized malonate to the kinetic resolution. Of course, a much better improvement is a dynamic kinetic resolution, where now you have a system where your starting materials can racemize between both enantiomers, and that in the presence of a kinetic resolution allows for a dynamic kinetic resolution, where now your inactive starting material can become your active one, and this can funnel towards your desired product in up to 100% yield. And a classic example from the literature and from industry is the hydantoinase process, where these hydantoins in the center here are racemized with high pH or with a racemase enzyme. And dehydantoinase can selectively pull out and hydrolyze dehydantoin to form these corresponding amino acid precursors in high yields and selectivities. And this is done for both natural and unnatural amino acids on large scale, even today, even though this process dates back to the 50s, I believe. So DKRs, as they're known, are quite powerful methods in stereoconvergent chemistry. Why aren't they used, I guess, more often? Well, there's a number of prerequisites, one being rates. So your racemization must be much faster than your slow reaction. Of course, we don't want to racemize our product, only our starting material. And then you're essentially running two separate reactions in the same pot. And so those two reactions aren't necessarily going to have the same conditions that they optimally operate at. So this is a huge issue and in terms of limitations for progress in developing new dynamic kinetic resolutions. And so the two main racemization modes applied to kinetic resolutions are that of proton transfer, where you have an electron withdrawing group next to a stereocenter that can undergo reversible proton transfer, and that hydrogenase process is a classic example of that. And then a little bit more recently is reversible hydride transfer, usually mediated by a metal catalyst. So Jan Beckvall was a pioneer of this. He first used Schwo's complex to reversibly racemize using hydride transfer this unsymmetrical alcohol, although it also works for unsymmetrical amines. And CalB, this Candida antarctica lipase B, can allow for the esterification of one enantiomer quite selectively, and they get very nice yields. But you'll notice that the racemization and kinetic resolutions are quite proximal to one another in terms of the carbons. So the kinetic resolution for proton transfer is right next door to where the racemization is occurring. And for hydride transfer, essentially, it's on the same carbon. And so this leaves behind a slew of cases where you could imagine a dynamic kinetic resolution at stereocenters beta, gamma, and delta, and so on from a site where you can do a kinetic resolution. And the issue is not necessarily with enzymes, because enzymes can recognize really remote stereocenters. So this example from Hedenstrom in 2002 shows that 8-methyl-decanoic acid with this very distal methyl ethyl stereocenter, it can be recognized by Candida rugosa lipase and selectively esterified with E values up to 25, yielding the corresponding ester. So the issue is much more with racemizations. And so, like Todd mentioned, we entered into this collaboration with the Macmillan Group, where we took a look at the budding CH functionalization literature mediated by photoredox catalysis. I don't have time right now to talk about how photoredox catalysis works, but essentially it involves a catalyst that can be activated by a photon of light and allow for oxidations and reductions in the same pot. But we took a look at the literature of CH functionalizations. And so on the left here is an older example from 2013 for the beta functionalization of ketones and aldehydes mediated by iridium photoredox catalysts and an enamine organocatalyst. And on the right here is a way more recent example of metallophotoredox to functionalize the beta positions of amines. And so we thought about the formation of these radical species as, while very, very useful for making CC bonds, CN bonds, and CO bonds, well, what if we, instead of having a somophile to couple these radicals to, what if we instead had a hydrogen atom transfer catalyst where our substrate also has basically a prochiral radical generated. And these prochiral radicals ablate a stereocenter. And so you can imagine in both cases, translating this to the following down here would allow for hypothetically new racemization protocols. And so this project on the left would be the basis for my project in the Heister lab, and the one on the right is potentially an interesting idea later in the future. Of course, this chemistry is quite new. But like I mentioned, this would be the basis for my project. And the way that this operates mechanistically is taking a ketone, condensing it with a amine, and forming this enamine. And then an iridium photoredox catalyst can oxidize this amine to the radical cation. And this significantly acidifies the beta position such that it deprotonates to form this allylic radical. Just before that oxidation, an excited state iridium, so this is generated through the blue light that's shown here. This reduces this dicyanobenzene species to this persistent radical anion. And these two radical species combine loose cyanide to form your corresponding beta arylated enamine, which then hydrolyzes to form your desired product ketone. And so, like I mentioned, okay, let's just replace the somophile with a hydrogen atom transfer catalyst. We generate our prochiral radical. And then the hydrogen atom transfer can occur with these thiols that have these weak SH bonds. So you form a thiol radical. This can be reduced by our photoredox catalyst and then protonated to conserve the proton that was lost originally here. And then you form your thiol catalyst again. And then, of course, you form your now racemized beta enamine, which can hydrolyze to form your racemized beta center. So that would be the hypothesis for this racemization. And with this hypothetical racemization, we wanted to, of course, pair it with a kinetic resolution. And so we thought the most straightforward answer would be to use stereoselective reduction to form the corresponding alcohol, or a corresponding alcohol selectively. And this is good because these alcohols can no longer form the enamine such that it cannot be racemized. And so we decided to use nicotinamide-dependent ketoreductases, which is, of course, a very well-studied class of enzymes. They operate by a substrate entering into an active site of a K-red. NADPH is the hydride shuttle that allows for the formation of the alcohol products. And essentially, the reverse reaction happens. And with excess terminal reductant, you form NADPH again and acetone as a simple byproduct. And so the scheme essentially was to first discover a kinetic resolution on a ketone substrate that had a beta stereogenic center, using racemic material, of course, and then to take that substrate, the enantiopure variant of that substrate, and develop conditions to racemize it using our hypothesized conditions with our thiol, our amine, and our iridium, or a photocatalyst. And then to combine both kinetic resolution and racemization to achieve a dynamic kinetic resolution, where we were specifically looking for greater than 50% yield, this threshold for kinetic resolutions. And so summing up some screening, we actually quite quickly found that beta-phenyl cyclohexanone, the substrate here, could undergo kinetic resolution quite nicely with the alcohol dehydrogenase from Lactobacillus kefir, LK-ADH, forming this RR trans stereoisomer with really, really good E values. And when we took the enantiopure ketone, what we found is that this iridium photocatalyst, pyrrolidine and thiophenol, allowed for the racemization quite readily in 4 hours. So we were really excited about these proof of concepts. The only issue was that they were run in quite different conditions. So you'll notice that the kinetic resolution is, of course, run in buffer, and the racemization is run in acetonitrile. So this presented itself to be an issue. And indeed, when we tried to combine the conditions in a biphasic manner, so using isobutyronitrile as our co-solvent for making it biphasic, we found that there was essentially no reactivity, and our protein was degrading. And when we took our kinetic resolution and added in each catalyst from the racemization, what we found is that the photocatalyst did not affect the kinetic resolution, the thiol didn't as well, but pyrrolidine was quite clearly killing or denaturing our enzyme. And this was attributed to the change in pH when we added pyrrolidine to the reaction mixture. And so we thought, well, maybe we can engineer a sort of hydrophobic amine organocatalyst, one that mitigates the interaction with the water layer and potentially form some sort of emulsion that would allow for productive chemistry. And so we began a different sort of evolution campaign for forming a suitable organocatalyst. So we first landed on this 3-OTBDPS pyrrolidine, and we were really happy to see that it had minimal effect on the pH and on the enzyme, and allowed for the racemization to occur in around 4 hours in aqueous conditions. The only issue is that we were getting around 80% mass balance recovered, and this is due to the formation of this reductive amination side product, which is a known process in the literature, where these ketones are taken, they can form the iminium, and they can be reduced to form this alpha amino radical, and this can undergo hydrogen atom transfer to form that side product. So we thought, what if we just introduce some steric bulk closer to where that chemistry might be occurring? And so when we chose this proline-based similar analog, and we found that our mass balance was dramatically improved. Somewhat less interesting, but just of note, we found that electron-rich and/or bulky thiophenols tended to lead to better mass balance and rate improvements. And so at this point, we were ready to see if our DKR could be achieved. And we found that first, purified enzymes allowed for around 86% yield of the formation of the alcohol in good selectivity. So we were really excited to see that. But soon after, we found that we could run a reaction in cell lysate, which is a much more preferred preparation of biocatalysts in industry and from commercial sources. And we also wanted to test if it worked in whole cells, and indeed, it does quite nicely work. But we decided to further pursue our scope later on with cell lysate, especially since we could just buy some ketoreductases from certain commercial sources. And just taking a look at rates really quick, the main takeaway that we found from examining the kinetic resolution is that we could get a KR over KS at around 74. And then in terms of our Racemization, our KRAC was around 4.4 times 10 to the minus 5. But most importantly, we found that the rule of thumb where in DKRs where KRAC over Kslow should be greater than 10 was indeed followed. We had KRAC over Kslow of around 11.7. So we were excited to see that matching or to allow for the DKR. So in terms of the scope, different substitutions on the Aaron ring work nicely. So electron rich, electron neutral, and poor substituents seem to work quite nicely. Pyridines worked with slightly mitigated yields, although the selectivities were still very nice. And then alkyl substituents, this homobenzyl substituent worked well for our chemistry, and then 5-membered rings also worked, although LK-ADH was getting us the cis diastereomer, interestingly. Of course, LK-ADH as one enzyme could only take us so far, and we wanted to see if it worked with other ketoreductases. And so we developed a screening method. So if we had a ketone substrate, we developed our own small panel of 32 ketoreductases, and we would run the ketoreductions on them in quite small scale, and then analyze them on HPLC. And we found that around 90% or so of the substrates had a viable kinetic resolution. We didn't know what absolute stereochemistry we were achieving with a given ketoreductase, but we could figure that out afterwards. But we could take that hit and run our DKR with a little bit of optimization quite successfully. And so these are some of those substrates. So a benzylic substitution on the 6-membered ring worked nicely using KRED P1A04, which is from Codexis. A mutant of LK-ADH, which we had from a separate project in our group, worked nicely for NBOC piperidones to form this corresponding cis alcohol. In terms of 5-membered rings, KRED P1A04 also worked nicely for this NBOC indole substituent. And this benzothiazole substituent worked nicely for KRED P2G03, which is also from Codexis. And so we are also able to form this intermediate. From our screens, we found an enzyme selected for the formation of this intermediate, which is en route to a complement factor B inhibitor disclosed by Novartis. And we were able to get it in good yields and very nice selectivity. And this was a dramatic improvement from the previous route, which involved 2 separate chiral resolutions. And we were also able to get a crystal structure to prove that absolute stereochemistry. And so, yeah, in general, we have this new racemization, and we can access the RR trans stereoisomer with LK-ADH. But say you wanted to explore chemical space and you wanted to access all of the stereoisomers, whatever project you're pursuing, well, theoretically, just by choosing the enzyme, you should be able to access each one with good yield and selectivity. And indeed, we found from our screens that these 3 enzymes, Prosomics 330, HL-ADH, and the same variant of LK-ADH that we had from our previous project allowed for the formation of all 4 stereoisomers. So we're really excited to demonstrate that divergence in our chemistry. And then theoretically, this protocol should work for any enzyme that functionalizes a ketone or an aldehyde. So transaminases, reductive aminases, aldehyde dehydrogenases, where R equals H, should work nicely for this chemistry. And indeed, in our project, we showed that transaminases do work. So even in the presence of 1 molar isopropylamine, and I believe it's 1 millimolar PLP, we can form these enantioenriched amines, which we follow up with Bach protection for analysis, getting good yields in these 2, getting good yields for the formation of these 2 products using commercially available transaminases. So just to conclude, I basically shown you that hydrogen atom transfer mediated by photoredox catalysis is indeed a viable biocatalysis friendly method for generating these prochiral radicals and racemizing in the presence of enzymes and for new dynamic kinetic resolutions. We're really excited to see what other CH functionalizations we can take forward to make new dynamic kinetic resolutions with the same sort of concept. And with that, I'd like to thank, of course, a number of people, Professor Todd Heister, as well as my group, including Andrew Meekin, who is working on the project. This project certainly could not be possible without the help from our collaborators, David McMillan, Dr. Kazunori Nagao, Dr. Young-Yao Lo, Matoshi Yamuchi, Jacob Kautsky, the research facilities at Frick Chemistry Laboratory, funding from the Ted Taylor Fellowship, and also Bristol Myers Squibb for their Graduate Fellowship Award, and for these sources for the enzymes that they supplied. And of course, for the opportunity to talk at this meetup. It's been wonderful. So with that, I'd be happy to take any questions that you might have. Thank you.
Great. Thanks so much, Jacob. We definitely have time for questions. So I'll pass it to Anthony.
Congratulations, a great talk. So first question from Stephen Wallace. Hey, Jacob, good talk. Can you account for the increased yield you see in cell lysate?
Oh, the increased yield? Well, actually, it's more about, not about cell lysate, but those results from the purified enzyme, those were pretty unoptimized. Once we figured out that we could use cell lysate, it's way easier to prepare that. We just kind of left that unoptimized purified enzyme result that we had, which we were quite satisfied with. But there's no issue with purified enzymes. So I hope that answers your question.
Maybe I could go for one, Jacob. So, like, great to see at the end there you extended your reactions to transaminases, which obviously you're running. I think it was in 1 molar isopropylamine. How does that? Do you still need pyrrolidine for the kinetic resolution process? Sorry, for the racemization process, and how does such a large amount of isopropylamine influence the photoredox cycle?
Right. So that's a really good question. So I think that that amount of isopropylamine probably would allow for the formation of the enamine to some extent, although I would say not as readily as something as nucleophilic as pyrrolidine. That said, it is quite interesting that we didn't see any isopropylamine reductive amination side product, which you would probably expect. And I think that really just boils down to the electronic differences between that, essentially the tertiary amine versus, or tertiary enamine versus secondary enamine. So that would be my thought, but we were really surprised to see that. I thought it wouldn't work, but it turned out to work quite nicely. Yeah.
Maybe I can go one more. If you so a lot, obviously you're working here often on the cyclic substrates. Can you envision, or are you already looking at acyclic versions of this transformation?
Yeah, certainly that was a substrate class that we were definitely interested in. We think that the formation of the enamine does not occur as readily, and so the racemization is dramatically slower. That said, I think with probably a better organocatalyst, I think we could certainly get it to work on acyclic substrates. It just would take a little bit of figuring out which sort of amine we would need.